so here we go. We have parametric functions today, guys. So pretty much in all of like your math, your algebra 1, algebra 2 stuff, you guys have always had equations with two variables, right? You had your x variable, your input variable, or your independent variable, and then you had your y variable, which is your dependent variable. So for parametric functions, that is now different. You're gonna have three variables now, right? So you are going to have two dependent variables. So x and y are both dependent on the one independent variable, t. And usually people use t because it represents time for a lot of like word problems. Not always the case, all right? But we're just gonna use t as our independent variable, all right? And these are called parametric functions. All right, so think of a parametric function as a function that has an equation for the x coordinate and a separate equation for the y coordinate, all right? So your function is gonna be x of t and then y of t. Okay, so your x coordinate is gonna have its own function, its own equation, and the y coordinate will have its own equation. And t is called the parameter. All right, and then at any time t, we know the coordinate point f of t by substituting that value of t into those two equations, and that will get you the point. All right, so let me go ahead and show you an example. So number one, at time t is equal to -1, where the parametric function f of t is given by this function, we want to figure out where is that parametric function when t is equal to -1. So guess what we're going to do? Plug it in. That's it. All right. So then x of -1 is going to be 6 minus -1 squared. So 6 minus 1 gets you 5. And then y of -1 is just going to be -1 plus 3, which is 2. All right. So then that means f of -1 is going to be at the point 5, 2. That's it. So that means at time, or when t is -1, that is the point you're going to be at on the graph. Okay? Pretty simple? Okay. So here, let's go ahead. I'm going to have you guys each take one, and then we'll go ahead and graph a parametric function. All right, so we're going to go ahead and graph this. We have a table. All right, I'll give you guys the easy ones. Milo, go ahead and get -2. All right, Jonathan, get -1. All right, Carter, 0.
Oh, that's great.
Megan, go ahead and take 1. Eason, take 3/2. And then Hughes, get 2.
Good.
All right, Milo, what'd you get?
Oh, I got -6 and 3.
Good. All right, and then this one I got -9/2 and 5/4. All right, Jonathan, what'd you get for -1?
-3 and 0.
Good. All right, and then this one will get you -3/2 and -3/4. Carter.
Oh, 0 and -1.
Good. All right, and then 1/2 would be 3/2 and -3/4. All right, Megan.
I got 3 and 0.
Good. And Eason.
Got 9/2, and I got 5/4.
Good. All right, and Hughes.
6-3.
Perfect. All right, go ahead and now let's plot those points. All right, so looking at this graph, right, that's the same function. Use the table of values in order from lowest value of t to the highest value of t. So moving from left to right on that chart. Go ahead and plot. I think this goes a little bit out, so this one's going to be 6. This will be -6. use arrows to indicate the direction of motion. So this is where parametric functions are different than what we're used to. This actually has an order based off of t. So using our arrows, we're going to go ahead and show that it goes in this direction. So we started at that one, and then we moved this way. Okay. All right, and that is your first parametric graph. Nice. Okay. Any questions so far? Yeah, Maya.
Wait, do we have to put an arrow on every single point?
No, it's just to indicate the direction of motion. Yeah, so that was probably more than you needed, yeah.
Do you take out points if we just add the arrow on the top, or do you
Like just this one?
Yeah.
Yeah, you should have some in, like, I would say those three would probably be the minimum. Yeah, so it's just to make clear the direction of motion. Okay, alright, cool, continuing. Alright, so this graph looks like a parabola, but we have more information now. Instead of just finding coordinate points, we know when the graph will hit each point and what direction it moves. Now there's no restrictions on this domain. In other words, there's no restriction on time, so this graph will actually continue on both ends, alright? But sometimes you will have a restricted domain, right, especially in like word problems. Alright, so you're gonna have a starting point and an ending point for that motion. So for example, that's what it'll look like. It has that restriction for t, alright? So you start here, and you end here. Okay, so use the table of values to sketch that parametric curve. Alright, and then we want to indicate the beginning and the end of this graph. Alright, so go ahead and plot your points on the graph for this parametric. Hopefully you guys are seeing. And then another parabolic. And we have our arrows going this way. Alright, so what is the point that's considered the beginning of the graph? Megan, what do you think? What's the beginning point for this?
0,
Yeah, 0, -3, so right there, 0, -3. Alright, and then Jonathan, what would be the end point?
5.
Yeah, that's it. That one right there. Nice. Alright, good job, guys. So that's the basic idea of parametrics, where you have those two dependent variable based off of the one independent variable t. Okay? Alright, kind of going a little bit into this one. This one, they give you the chart and they want you to decide which function, which parametric function is used to construct this graph. Okay? So looking at these, well, actually notice all of these are linear, right? Look at these options, these are all linear. So you just need to find the equation of the line that gets these points and the equation of the line that gets these points, right? So because it's linear, I'll start with the x. I can go ahead and just find the slope, right? Here, see -3, -3, -3, -3. So that has a slope of -3. And I could also find my y-intercept right here, right? That's when t is 0. Alright. So based off of that, I'm either option A or option C. Okay, go ahead and do that for the y-coordinate and then decide which multiple choice answer is correct. Alright, and which one do you guys think? C, yes, is correct. So this has a slope of 2. thought? Yeah, okay, good. All right, let's go ahead and talk about the rates of change when it comes to these parametric function. Like how is it changing, especially because we have those arrows, all right, kind of makes things a little more interesting. All right, so as the parameter of t increases, the following conditions apply. If x is decreasing, right, just think about x as horizontal motion, right? If it's decreasing, that means it's going to the left, right? As x is decreasing, your parametric function is gonna go to the left. It's increasing, it's gonna go to the right. So what do you guys think about the other ones? If y is decreasing, the particle is gonna be moving down, and then if it's positive, or y is increasing, excuse me, the particle is moving up. Hopefully that makes sense, right? X horizontal direction, y vertical direction. All right. So again, this is over an interval of increasing values of parameter t. Okay. All right, let's see. Because we're able to model the horizontal and vertical component of the particle motion using these functions, it follows that any given point on the plane, the direction, highlight this, the direction of the planar motion may be different for different values of t. All right, so we're gonna see this in some of these examples, all right? So what it means is that as time increases, the direction of motion can actually change, all right? So it might not just be constantly going in this, it might change direction depending on what part of the function you're on, okay? So like circles, parabolas are good examples. All right, so let's go ahead and look at a circle example. Okay, so we have this function, parametric function. All right, we have cosine of t for x, sine of t for y, and we're just doing from 0 to 2 pi. All right, we already have the chart here. So we're gonna examine both x and y on this interval from 0 to pi over 2. All right, and we have our graph over here. We have our table here too. So here, as t is increasing from 0 to 2 pi, what's happening to our x values? Is it increasing or decreasing? Decreasing, right? It's going from 1 to 0. And on the graph, you can see this too, right? It's decreasing, going this way. All right. So then, is the particle moving left or right based off of that? Left, right? Good. All right. So then you would say it's moving left because x of t is decreasing on that interval from 0 to pi over 2. All right. So it's moving left because it's decreasing. All right, so next, is the particle moving up or down on that interval? So take a look at that, those y coordinates. And Milo, what do you think?
It's moving up
Good. All right, because?
because y is increasing.
Yes, nice. So y is increasing, so it is moving up. Up. Because y of t is increasing on that interval. All right, nice. So these two graphs are graphing x of t and y of t separately. What does it look like on the parametric graph? So the parametric graph from 0 to 2 pi is from here to here, right? So notice it is moving up, like we said, and simultaneously it is moving to the left, just like you guys said. Left and up. Okay, so on the parametric function, it is moving up and left. All right, good job. Okay. So a curve can be now parameterized in different ways, all right? You might have the same curve, but you might have different t's, different directions. So I wanna show you guys how that can change. So for example, this particle's position and motions are modeled by this over this interval, and they already graphed it for you, right, going in this direction. So let's go ahead and draw in those arrows to help us see that direction there. On the interval from -1, t is -1 to 2, right here, let me highlight that, -1 to 2. We see that it's going to left and up, right? It's going left, and it's going up. From the interval from 2 to 4, we see that it's going right and up. Alright, so we see that change in motion. Now, we might have that exact same curve, but maybe t goes in a different direction. Alright, so let me show you that. So this, different function, right, than that. Okay. We can see that this is actually the exact same curve, but it's actually going in the opposite direction. Alright, so this one is going in this direction. Okay. So on that interval from -4 to -2, it's going left and down. And then going from -2 to 1, going right and down. Alright, so I want you guys to see that side by side. So same curve, but notice it changed the directions, okay? And different parametric functions will do that. All right, so how can we actually use this, right? Like how, if I have this, how do I get to that, okay? So that's what this box is for. Change the direction of a parametric function, all right? So if we want to keep the same curve, but change the direction, all we actually have to do is plug in -t into the original functions. Right? You plug in -t, and I'll give you the same curve, but just opposite directions. If there are restrictions, the restrictions will flip also. So it'll be from -b to -a. Okay, so let me show you an example of that in this little tiny area down here. So for example, if I wanted to, let's say if f of t was t minus 2 and 3 minus t, we'll keep it simple, alright? And I want to get the same curve, but different direction, alright? And we'll say on restricted domain, -5 to 6. I'm going to try to find what would give you the same curve or same graph, but opposite direction. Alright, so if I wanted to do that, I literally would just plug in -t in for my x of t and my y of t. So then x of -t would be -t minus 2, y of -t would be t plus 3. Alright, so then that would be my function. Alright, so then f of -t would just be -t minus 2 and then t plus 3. On the domain is be -6 to +5. Alright, so that would get you the same graph, just going opposite directions. doing okay? Yeah, all right, cool, good. All right, just one last thing I wanna show you guys, and that'll be it for parametrics. All right, the last thing I wanna show you is just the average rate of change. All right, so we've done average rate of change a lot, right? So it's like rise over run, that idea, change of y over change of x. All right, so we can do something similar to parametrics, but what we're gonna do is we're gonna do x and y independently, and then we're gonna ratio those to find the rate of change for the parametric, okay? So then this change of x is gonna be x of t sub 2 minus x of t sub 1. Oh, sorry, I don't know why I made that so small. Resets. There we go. Over t2 minus t1. And then y will be y of t sub 2 minus y of t sub 1 over t2 minus t1. And then your final slope is just gonna be the change of y over the change of t over the change of x over the change of t. Okay? Yeah, a lot of times those chains of t's will divide out. All right. Cool. Let's try. I wanna have you guys help me with these. All right, this is just calculations. All right, so number 3, use the parametric function, okay, over this interval to find the following. The average rate of change of y of t, so careful there, just y of t over that interval. Okay, let's see, Carter, give it a try.
Oh, is it like y of like the t? It's the second t, right? So it's 0.
Oh, it doesn't matter, yeah, sure, 0.
Y0 minus y negative 3
Mm-hmm.
over 0 plus 3.
Mm-hmm. Keep going. Go ahead and plug it into the function.
So,
Do it.
So y0 is like 3.
Yeah,
and
that's
then
just 3.
Y negative 3 is 0. Or,
Mhm.
yeah, 0.
Yeah.
And then it's just negative, or plus 3, yeah.
Mhm.
And then so it's just 1.
Yeah, nice, that's it. So plugged in 0 into the function, you get rad 9, which is 3. Plug in negative 3 into the function, that's rad 0, so that's just 0. Nice, okay. So that's the average rate of change of just the y coordinate. Okay, let's go ahead and do the same thing for the x coordinate. Eason, give it a try.
Oh.
Do the same thing
so-
just for x of t.
So x of 0
Mhm.
minus x of negative 3
Mhm.
over 0 minus negative 3,
Good, uh-huh.
and that should be equal to well,
2
plug
times
in
0.
you plug in 0 into the 2t, so it's 0.
Uh-huh, good.
Then
Got me word there, uh-huh.
negative 6, so minus negative 6
Good, yeah, okay.
over 3,
Mhm.
which should be equal to 2.
That's it. Nicely done. All right, Easton. Okay, and then part C. So the slope of the line between the points found using those, all right, on the parametric function should then be what? Q's.
1 over 2.
That's it. You got it. All right, so change of y over change of t. Change of y over change of t gets 1 over 2. Done. All right, good job, you guys.